And thank you all for joining this open office hour. It's great to be able to continue this series, and I'm very happy to see people joining in. So I hope you're all well. That's first and foremost. In terms of importance, and the second in importance is the question of what it is that we're going to do during this hour. So I will talk about online databases of behavioral data. And of course, the motivation is very much the same as the motivation for the previous office hours. That is to give us the tools to continue our work, extend our work, even as the labs are closed. So let me share my screen, and then we'll get started with the actual content. Okay, let me see how right. Okay, so perhaps the first question to ask is what kind of resources exist and how to look for them. And I have shared in the abstract for this office hour, I have shared a link to an excellent list of resources for the so-called word mega studies. So Mark Brisbert is the one to compile this list, and quite specifically, it has resources across languages, multiple languages, of existing behavioral databases with chronometric data. Yeah, so you will see here resources with word naming, latencies, lexical decision times, reaction times, some eye tracking data, semantic classification, some progressive demasking, and so on. These only include resources that have the data actually available, as opposed to links to papers that only describe a resource rather than making it available. And you will see that this is an excellent and a very broad list of what we can use straight away. So I'm going through Chinese. There's Dutch with lexical decision, both visual and auditory. There's another lexical decision data set in Dutch, speeded fragment completion, text reading with eye movement data, word recognition times in the vocabulary test, very close to lexical decision. And now we get to the list with English resources. And this is really what we will spend most of our time looking at. So some of these resources are such that they have an interface, sort of a user-friendly interface that allows you to interact with the resource and either extract some data from it or ask questions. And if you ask nicely, this resource will give you the data that you're looking for. So I will start specifically with the English Lexicon project, which is perhaps the first resource of its kind. It's created by a group of authors with Dave Bellotta as the lead. And you have a link to the actual paper, but we'll start with the link to the data. So I'll just open it in a different tab. So here it is, English Lexicon Project website. You will see that it contains visual lexical decision and naming data for 40,000 words and an equal number of non-words. You have the number of participants and measurements here on the website. And even without working with the actual data, even without getting access to the spreadsheets or tables that constitute the actual content of this data set, you have some interface that allows you to do a few things straight away. For instance, you can use this to generate lists of words with specific lexical characteristics. And this is because the English Lexicon project has rich annotation on a number of lexical variables. So its main goal, the main goal of these resources, and really of all resources that we have looked at so far, The main goal is to provide chronometric data, most reaction times, but they also bring in, and most resources bring in a bunch of variables, lexical variables of interest that, strictly speaking, they did not collect. They just compile it together with their chronometric data. So we can go to semantic variables, and you will get access to concreteness ratings and semantic neighbors and age of acquisition and emotional variables and several others. You can select, well, let's do age of acquisition, use this function as a filter and enter the minimum value and the maximum value that you're interested in. So say you want words that are learned between the age of 5 and 8. You submit this constraint. You can, of course, select multiple constraints, and once everything is said and done, you can send this query to an ELP lexicon, the English Lexicon Project Lexicon, and get the results either in a browser or email. So, oh, the query generated no results. Well, because I played with this resource a little earlier, I had more restrictions on length and so on. If we remove them and do our query again, then hopefully we'll get some results back. It does work, this resource, there's no doubt about it. It's just a matter of selecting your criteria correctly. Okay, so again, I must have restricted it in some other fields. But let's not spend a lot of time on this, because this is an interface that you can study on your own and get an idea of how to generate lists and how to get the lexical decision data from these lists. What I want to spend more time on is how to download and use the actual data from resources like these, and how to be able to filter our own data and create our own lists of stimuli, and effectively create what we will call virtual experiments. So these are experiments that rely on existing data, but because we build in manipulations to the stimuli, we select the stimuli in such a way that they demonstrate some contrasts in lexical variables that we care about. We can use the response times in the way that will be similar to running an experiment of our own in the lab. So what I will do is show you the British Lexicon project. This is lexicon decision data to words in English collected from a British cohort of mostly students. The data is for 28,000 words. And if you follow the link, this will bring you to all the lexicon projects that were created by Emmanuel Kohlers, Mark Brisbert, and their team. We are particularly interested at this point in the British Lexicon project right here. And more specifically, we will look at the average reaction times and accuracies for stimuli. You can get access to the trial by trial reaction times. So the trial level data will give you access to every response by every participant to every stimulus. And this will be, I'm sure, very interesting if you are into either individual differences between participants or the effects that the progression through a study has on responses. We will do a simpler thing. We will just work on average reaction times per word and reaction times and accuracies. So different formats are available. I downloaded the one that is specifically designed for working in R. Okay, so generally you will learn in this hour that most of the work on running virtual experiments on using these existing online databases is that of putting a puzzle together. So what we do is search for the resources that we need to answer our questions. we have, of course, to read these papers to figure out what variables are represented, how they have to be collected, how they were collected, and how we have to use them. This is the this is the part of our job that nobody will take away from us and nobody will do for us. But once we have this knowledge, the rest is just combining these pieces into one puzzle. So what we'll start with is I'm opening an RMD file. And generally in this hour, I will be relying heavily on what Pablo Gomez presented to us in the previous Open Office Hour. So that was an excellent presentation. If you were not for it, if we weren't around for it, I recommend that you look up its recording. But so it taught us two things. One is to use a specific type of an R file called, it goes under an RMD extension. And this allows for nice representation of both the code and the text. And secondly, he taught us a library called Tidyverse, which will be very useful for our purposes here. So you have both these files and its PDF version and all the data materials that I will use. You will have it on the OSF Open Science Framework repository right here. So under Open Office Hour, you have the zip file with all the data, as well as the files that I'm going over right now. Okay, so first off, I'm giving you some of the links to resources, where to look for them, where to find them. And then what we will do is read files of the British Lexicon project, namely the mean lexical decision response times, as well as stimulus characteristics, and we will select some columns of interest. The first few lines of code are just uploading the libraries that we will use later on, and of importance is the Tidyverse library. And then we're moving to the next chunk of code, starting from line 32. And once we have downloaded the files that are made available on the website that I just showed to you, we read them in, and the way to do it is by running a load command. And then this will load the information about items. And I will move this a bit just to show you in the top right corner of the screen that we have just read 55, almost 56,000 observations with 8 variables, with 8 columns in them. So click on that and you will see the structure of this file. It has spelling with the actual word in it. It has column lexicality with 2 values, one for non-words, another for existing words. RT is self-explanatory. Z-score is the RT that is standardized or Z-transformed. This, of course, is the mean response time for that word over all participants who saw that word. We have an accuracy, standard deviation of response times over participants, and some other things. So this is what the file comes in as from the creators. Okay, and it is our job to change it or rename the columns in the way that we want. Now, you will notice that in the British Lexicon project, we have separately the response times data with words, of course, and stimuli characteristics with, say, length and frequency, and all these things are actually separate. So they are presented as a different file, which has a name of VLP stimuli. If we look at this one, we will see spelling as the same column as we saw before, and then a bunch of lexical variables, including, say, the number of letters, the number of syllables, a morphological category, flexion, syntactic class, frequencies of all kinds and fashions, and so on. So there's 22 columns, and again, it is our job to look at what they are and figure out which of them we want actually to use. So these are 2 separate files. We need to bring them together because ultimately we will want to look at the effect of some lexical variables on response times. Right now they live at different files. The one column that allows us to merge these two files is the column that these two files share. It's called spelling, and it's actually the spelling of the word. So in line 42, we use one of the commands, one of the functions of the tidyverse library, which has a name of inner join, inner_join. We provide as an input the two data frames that we just read in, VLP items and VLP stimuli, and we have to specify the column or columns that we want to merge these two files on. So in this case, both the first file and the second file have spelling as the name of the column, and so the merge command or the join command will use that column in both files to bring together their contents. So what it will do is quite literally take a word like well, these are all long words, so it will take a non word like a bear with all the response time data and look up the characteristics of this word in the other file and bring them as columns in the same data frame. So that's what merge does. Now, inner join is just one of the several options that the join functions have in tidyverse. And what it says is that it will require matches from both sides. So if either of the files does not have a certain spelling, this spelling will not make it, this row will not make it into the joined file, into the merged file. There are other options like left join and right join, and we'll get to them a little later. Okay, so we use the inner join, we get a BLP as a result of it. That's the merged file. And it has, as you will see, the same number of observations and 29 columns. So 29, of course, if you add up 8 and 22, you get 30. And spelling is a shared column, so it will only be represented once. So 30 minus 1 gives you the 29. Okay, so the next thing we'll do is select only some of the columns. We will probably not need all the 29 of them. We'll select some of the columns using the select function of tidyverse. And we will rename some of the columns. I'm doing it because I'm more used to some names rather than others. Before we do that, we're defining a data frame that will contain the output of this function. I'll call it blp.small. So the arrow, of course, shows that the output will be saved into this variable, into this data frame. Then we take the data frame that we want to modify, and pipe is a function in R, in tidyverse, that tells us that we will take this data frame and modify it in some way. Okay, so select would take a column called spelling and rename it as word. I rename lexicality as lex. We're keeping in RT and Z-score without changing their names, and accuracy. I'm renaming number of letters into length, and I'm keeping some of the other variables in their present form. Now that we've done it, we can look at the summary of this new data frame, and it will give us information about the distribution of values and so on. Okay, so in the column for RTs, and let me move this a little further up, you will see some number of observations that comes with NAs. So apparently these are not really defined. And you will, of course, see in the summary of the column lex that about half of the words have the similar are non-words coded as N, half are actual words coded as W. So in the next bunch of lines, in the next function command, we will remove bad responses. Bad responses is defined here as an RT not defined. So an NA in terms of RT. We'll also remove outliers RT, and for that we can use the Z-score. So if the standardized RT is further away from the mean than 3 standard deviations, we can remove that bit. And let's remove non-words as well, so that we only work with existing words. So we do this with a bunch of filter functions, and again, this has all been presented by Pablo, so I will go a little quicker here. Like Pablo, I like using a separate filter function for each modification that I do to the data, and the pipe command is making it so that the output of the previous modification becomes the input for the next modification. So in the first filter, I'm removing RTs that are NAs. In the second filter command, I'm removing Z-scores whose absolute value is greater than 3. Well, to be more precise, I'm keeping in the Z-scores with absolute value smaller than 3. And I'm keeping only those words that are actual words. So Lex is W. So we run this. So BLP small is a considerably smaller data frame because we lost, well, all non-words and a few more things. And this is then the data set that we have so far, and we will work with this. Before we do so, let's do some data transformation. Frequency is given in absolute counts. We'll probably want to log transform it. We will also want to transform, or at least have different ways to transform the response times, because it is supposed to be skewed, and it's very likely to be skewed. So in line 65, we begin some code that does transform the data. This is done with the mutate function. And what we do is create a new column called lfrec for log frequency. We take a log of what is now coded as column frequency plus 1. This is a common way of getting rid of the 0 problem. You cannot take a log of 0, so you add 1 to each count. We can also create a column called inverse RT, and this is how we do it. And we can create a column called log RT, which will be a log transform response time. Okay, so we do this. And if we now just click on BLP small, you will see all these new columns added to our data frame. So they're now available to us. Let me remove this. Okay, so let me stop here for a second and ask if you have any questions so far.
If anybody has anything they'd like to ask at this point, feel free to unmute yourself, or alternately, you can enter it into the chat at the bottom of your Zoom screen.
Give it another 5 seconds, and then we'll proceed. Okay, so you will most definitely have more chances to ask questions later on. Okay, so now we have BLP data, transformed and cleaned up and ready for use. Let's bring in some lexical variable that this specific data set does not have. This will be another piece of the puzzle, and almost randomly I chose to use South Florida free association norms for single English words, and I give you a link for where I obtained it. The original file type that you will download from this resource is CSV, or comma separated. And so we read this file with the read.csv command. Okay, so if we open this this data frame in the viewer that RStudio provides, you will see a bunch of words that serve as cues. And effectively, the way it worked is that a large number of participants were getting these words one at a time, and they would have to produce as many pre-associations as would come to their mind within a limited time frame. So the first column, QSS, is the number of associations that they produced. So abdomen has 12 associations, and above has 9, and accelerate has 11, and so on. And of course, there's a bunch of other information available in this data frame. They are all explained in the paper that comes with this that reports this resource. Okay, so we'll do another piece of the puzzle. More specifically, we will take the raw data that we just read in, the association data. We'll create an association a SOC small data frame, which will select just some of the variables from the original data file. And so we select and we rename. So I take Q as the original column, save it as Word. I take QSS, which is this set of associations, and I save it under association neighbors, which might be not an optimal name for it, but this is what I have. Okay, and so we do this selection, and just to show to you that this is possible in one and the same command, after this selection is done, we use another pipe. So the modified data frame becomes the input to the next function. And more what we do in this filter statement on line 81 is take all columns that well, we only retain the columns that do not have an NA in the association neighbor column. Okay, so we prepared our data in such a way we now have 4,001 observations, lost some 400 observations from the total, and it now has only 2 variables because we only selected the 2 variables. Okay. Now we bring together lexical decision and association norms. So our BLP file that was cleaned up and ready for use was available under the name of blp.small. Now we have association.small. We renamed the columns, the original columns, in such a way that they happen to have the same name, word and word. It doesn't have to be like that, but right now we have the column on which the 2 data frames will be merged. These columns have the same name in the 2 data frames. I chose to use inner join here, which will again mean that only those words that are represented in both files will make it to the merged file. There's some warning that we can ignore. More importantly, we have a lexical decision and association merged file with some 3,000 observations. And now that we have it, we can analyze it in a lot of ways. So one thing that I like to do is look at the correlations between numerical variables. So what I do here is use a function called pairscore, so pairs correlation.func. It comes from a language from a library language R, and this is one of the libraries we uploaded in the very beginning. And all it takes as a data is the data frame with the columns that we're interested in seeing the correlations of. So if we run this command, what we get is a plot right here. I know it might be too small for you to see, but on the diagonal we have the names and the distributions of the variables that we chose. So for instance, we see that the distribution of our association norms is pretty symmetric, which is great. And the distribution of log frequency is fairly symmetric, which is also good. That's why we transformed it. Then in the above the diagonal, you see scatter plots with some trend lines for every pair of observations. So we have RT in the first row and the first column, and this is a scatter plot showing the relationship between the RT and the inverse RT. This one is a relationship between an RT and accuracy. So that's the intersection of the first and the third variable. And you can see that when the accuracy is low, the RT is large. And as accuracy increases, the RT decreases. Then we have correlations with length, the scatter plot with length, log frequency, and association numbers. And and below the diagonal, you see the actual numbers for correlations, both the Pearson and Spearman correlations, which tell you exactly how strongly these lexical variables correlate. So, for instance, for association neighbors, we see that they correlate. We see in this, we see at the intersection of the first column and last row, we see a correlation between RT and association neighbors, which is a relatively weak negative correlation. So the more association neighbors we have, the lower the faster the responses are. So that's a correlation table. And of course, now that we have the data, we can do all kinds of models with it. This, so far, as we have the data now, this is a so-called regression design, meaning that we have a bunch of numerical predictors, and maybe one of the things we might want to look at is whether this association data explains any variance over and above controls, and if it does, what kind of effect it has and in what direction does this effect go. So this office hour is not really about modeling. We'll have this separately. This office hour is about how to get to databases and combine them together. But just for the fun of it, let's run a simple regression model, a linear regression model, with RT as a dependent variable and a bunch of control predictors, length, frequency, morphological class, syntactic class of the word. And in this first model, we do not have the critical predictor of association, number of associates. So we run it, this model, we'll look at its ANOVA, and we see in the p-values that all these predictors are very, very strong. So they explain a lot of variance in the response times. We can, in line 103, we can look at the adjusted R-squared just to see how much variance is explained before we included the association neighbors. So some 39.1% of variance is explained. And now we can run a second model which has the same controls plus the new variable. We'll look at ANOVA and see that this extra variable is indeed a significant predictor of response times. We can now run a summary and just look at the R-squared. And we're now explaining 39.2% of variance. So the previous one was 39.1. So we get about 0.1% extra explained by associates. And ANOVA with the two models will compare the models by the amount of explained variance, and it will tell us whether this extra variable that we just added with associates is worth the investment, and indeed it is. So we have some evidence that this was this variable does some work. Let's plot its effect. For this, I'm using a library called Effects. It's one of those libraries we uploaded in the beginning of this session. And to draw to visualize an effect of just one predictor, we use effect as a function. provide a model which contains this predictor and define the name of this predictor as a focal predictor. We can have more than one, but for now we're just doing this one. And here it is. So we can see that a small number of associates comes with longer response times. A large number comes with a with a faster response time. And the overall range of the effect is on the order of 10 milliseconds. So not the strongest effect, but good enough for this demonstration. So that's what we can do in a few minutes of analyzing, downloading, and analyzing the data. And I encourage you strongly to do exactly that. Let me stop for a second, and before I go into a different data set, I'll check the chat now in case you have any questions. I can figure out how to open it. Right, okay, so when you combine databases based on the actual stimulus word, what happens to A, overlapping words from each database, identical words, and B, new words unique to each database? Okay, so starting with A, it might of course happen that one and the same word is represented multiple times in a database. In fact, if we will look at the trial level data, we will have the same word repeated as many times as we have responses to it. So for every of these multiple occurrences of the word, the merge will bring in the lexical variables data to each row. So for each occurrence of a word house with response times, if we merge on the word, we will have the lexical characteristics of this word house repeated as many times as there are occurrences of house in the data frame. Okay, then question B, new words, what happens to new words unique to each database? Right, so far we use the strictest kind of the join operation, which only retain the words that occurred in both data sets. If you can use different ones. So there is a function called left join, and this will retain all the words in the left data frame, regardless of whether they have a match in the second one or no. So in this case, the word which has an RT but not lexical variables will be retained in the merged data file, and it will have the RTs still, but it will have NAs for all the lexical variables. And the right join will do the same thing, only it will retain, the words all the words in the right data frame, and it will put in NAs for whatever is missing in the first one. Okay, let's move to the next question. More general question. If you were to publish your analysis, how would you write your methods? Do the paper from which data comes indicate how to do it? Right. So you would of course cite the sources, right? The papers that reported the
okay, you can come in.
The data sets that you used. Then in the method section, I tend to give very brief information from those original papers on how their data was collected. Yeah, just whatever is relevant for the present analysis. But then we have a luxury to just refer to those original papers and say, you want to know more about their method, look it up. Okay, so all we need to do is say we took some words from those original source data sets, and then we proceed with our paper. Yeah. Okay. Good. So let's move on. This is just to show that we can move on with our puzzle even further. And what I did was take a semantic decision data set. It's also described. Let me move back to here. This is a data set that Penny Paxman and her colleagues have reported. It's a semantic decision data where people saw 10,000 words, lemmas, and they had to decide whether the word is concrete or abstract. And response times were recorded, and the data is available here. So this is just to show that it's equally easy to analyze multiple data sets and bring them together. So the original data set comes in as an Excel file. So we use a slightly different function to read it in. So we call this a semantic decision data set. We can look at its summary just to familiarize ourselves with what is being offered here. The most important things for us will be, of course, the word itself, which goes under word capital W. And we will use RT clean mean, which I take to mean that, well, this is an average RT after the data was cleaned in some way, and so on. Okay, and there are a few more variables that we will take in. Okay, so this should be familiar by now. We select just the columns that we want to. And by the way, if you have second thoughts and want to add an extra column or remove a column, you can always change this code every which way. So we select words, we rename them in the way that I tend to prefer. Oops, and let me run this line. Okay. Then we go back and merge semantic decision with association data. Okay, so we just created semdec.small. We have the association.small. We use an inner join here just to retain the words that overlap. Okay, and what we get is a much smaller set, but it has emergent information on both with words, NRT, and accuracy, as well as concreteness. All of these came from the semantic decision dataset plus association neighbors, which came from the association data frame. Right, so because of the way that Excel files are read in, I have to do a couple more transformations just to make sure that the RT and concreteness ratings are treated as numeric. Next line does a mutation, so the transformation that we previously did for the lexical decision data. Now we do it for semantic decision data, and I'm doing two of them because different people prefer different transformations. So we create an inverse RT and we create a log RT based on the raw RT. Okay, there we go. So so in this data frame, we're missing a bunch of lexical variables. We have concreteness and we have the number of associates, but we can do better than that. So we're missing length and frequency and other variables. So what I suggest that we do is bring subtitle word frequencies for English from this data. And I provide a link to where to find those frequencies. We can also bring in affective ratings from Werner et al. Ratings of valence, which is, well, positivity, arousal, and other things. So the next few lines are just reading in the data sets with frequency. Again, because of the quirks on how data is read from an Excel file, I need to convert frequencies into a numeric variable. This is done in line 152. Then, and this is saved in a data frame called sublex for subtitle lexicon. We mutate frequency, we change the frequency in the way that we considered before, and we select only two variables, word and frequency, or log frequency. What Yeah, what we now do in line 156 is use a different join. We use a left join. So 2 data frames, one has semantic decision with associates, and the other one has subtitle frequencies. Now we use left join to make sure that everything that we have in the left or the first data frame here is retained, right? If there's no match between these 2 data frames, then we will simply not get the frequency for some words. They will be filled with NAs, but we won't lose anything from this data set. And right, and please note that in this time we have different names of columns, right? So in the left data frame in semantic decision, this is a lowercase word, and in the second or the right data frame, it's the capital W. So we merge them while taking count of the different spellings of the column names. Okay, save them under the same name as the associate. Now we read effective data, which I just downloaded. From this data, affect, we select valence, arousal, and the word. And what we see here are the original names of the columns that you can always look up here, both here in the data frame and in the paper, which gives the legend for what different variable names stand for. So we select these, just these columns in effect small, and we do again a left join, this time with effect small. Left join means again that all the data points from the left data frame will be retained, and we're not sure about the ones from the right one. Okay, so like pieces in the puzzle, we brought in frequency and effective data. We can look now at the resulting data file, which now has everything that it had before, plus log frequency and valence and arousal. Okay, we're still missing word length, and this is easy to do. So we mutate. So we create a new column called length, and we just use a basic function in R called an nchar, or now the number of characters for word. Okay, and we can do a histogram of length here. Shows in our PDF file. Okay, let's say we want to remove very long words. We filter out words that are 10 characters or more, and yeah. And once we've done that, we are ready to use our data frame that has both semantic decision times and association and some other variables. In the interest of time, I will not walk you through the entire models. Well, you will see, however, that there's no effect that association neighbor has on semantic decision response times. Okay, one last thing that I want to show you before we move to the questions, very quickly. Say we want to summarize, to aggregate the data in some way. So here's an example of how we go back to our lexical decision time. And let's say we want a table that will have a mean response time for every word length. So how long on average do we read a 4-character word, a 5-character word, and so on. So we take blp.small as the data set that we created. We group it by length. What this means is that every operation from now on will be done to words that are grouped, well, that are binned by length. Okay. So, and we use another function that we haven't looked at yet, function summarize. We create a column named rt.length, and we take the mean of response time. So what this will do is, because we're grouped by length, it will look at the mean response time for every word length. And we have another one, another function here. I'll just move it quickly. So n is n. So n with empty brackets is simply taking a count. How many words do we have that have a given length? And we store it, well, perhaps I should give it a slightly different name. We'll store it into a column that we'll call m length. So if we run this, we get length summary. The new data frame, and what it shows to us is that, well, the average response time for 2-character words is about 595 milliseconds, and for 3-character words it's 607, and for 4 characters it's 617. And in the column number of n length, it gives us the number of words corresponding to each length. And for 13-character words, we only have 1 word in that data frame. Okay, so now we can plot the length and the RT, and we will see that there's virtually a linear relationship between how long a word is and how long it takes on average to read. Okay, so I have some other smaller things, but they are all really variations on the same theme. So you'll have access to this file, and you can work through them on your own. I think it's best if I stop here and ask you. Well, you're very welcome to ask me questions. As always, I'll be available on email to ask you questions if they come after this session. So over to you now.
If anyone has any questions, now's the perfect time to ask. Feel welcome to unmute yourself if you'd rather ask in, using your voice, but of course you can enter it in chat as well.
Right. Okay. What are the differences between Sufflex US and the English Lexicon project? So Sufflex US is a frequency list based on subtitles to films and media in the US. The English Lexicon project is a database with response times and accuracy to lexical decision data. Now, the English Lexicon project now incorporates a bunch of other variables that have been collected, after the English Lexicon project has been created. And I believe that Supplex frequency is one of those. So as are, concreteness and balance and so on. So the difference is in the type of variable that these two were created, that these two projects were created for. I believe that the English Lexicon project now incorporates more and more of the lexical variables that have been collected separately and independently. Okay, can you give some examples of published experiments following the approach you went over? Yeah, well, I'm primed by what I have been doing, so it doesn't mean that that's the only example that we have. But I have a paper published in, I think, 2015 on virtual experiments, where I looked at just the secondary data, lexical decision and valence and arousal, and I considered a bunch of lexical variables collected from all kinds of sources, and yeah, so that would be one of the very many examples where this is done. And I will put some copies of the papers that I can think of on Open Science Framework so that you have access to it. All right. Right. Can you tell us a little about the databases with eye tracking data? Do they present fixation data for lists of words, or is there info about the context? Right. So some of these databases are amazing. Well, they're all amazing, but some of them have information at the word level for every word in a sentence. So we get to know their position in the sentence, the context that preceded them, and so on. One such resource that comes to mind is by the first author is Ushib Kop, has been collected in Ghent, and the gecko, right? So I'm just typing it in the chat. Gecko is the name of the corpus. It's been collected from English and Dutch readers in their first language, and from Dutch readers reading in English as their second language, and you have very detailed data for every word, but also for context. The Dundee corpus has context as well. I mean, yeah, so most of the eye tracking corpora will have extended context presented with them. Okay, is there any possibility to find an open source database, including psycholinguistic characteristics combined with EEG measures? I have not specifically looked into that, but what I suggest that you do is look up the list that I advertised, the list compiled by Mark Brisbert. Well, and we can do it together now very quickly and see if EEG appears. Oh yeah, so Winsler 2018 go no go EEG measurement. So there's a reference here, and yeah, I believe it's yeah, and there's a go no go task with EEG measurement. There's sentence reading with EEG measurement, Frank et al. 2015. So look up these resources and see if they made their data available.
Victor, it's Gary speaking. I have a question for students or for supervisors whose students are not able to engage in laboratory research at this time. What's your sense of like how, to what extent have these resources been used? In other words, how open are the opportunities at present, say for students, right like this month?
Right. Okay. So I should mention that all the resources I talked about now and all the resources presented in the list or the lists that I refer to, they are open today, and so they can be used immediately. I think that, well, let's put it this way: there has been a lot of use of some of these resources, but they're still heavily underused, right? So definitely in some tasks like lexical decision or word naming for some languages, like perhaps English and Dutch, there's no reason not to engage in cross-linguistic research today. So there's effectively everything that, well, there's never everything, but there's a lot that is available at this very moment. With other tasks, it's perhaps a little less luxurious, but still possible even with eye movements for some languages. Long story short, please start working on this today, because there's a lot of potential in this, and not everybody has tapped into these resources who could have.
Thanks.
Okay, great. Thank you so much, Victor. We're at 1 o'clock now. I would recommend that any follow-up questions be sent to Victor directly by email. He's very welcome, very welcoming to questions in that format. So if you have any comments, feel free to email us at the Words in the World grant@gmail.com account that we've been sending out announcements with. If you know anybody who could really benefit from these open office hour sessions, feel free to ask or recommend to them that they contact us, and we can add them to our mailing list. So thank you everyone for coming. I hope you have a great week. Stay healthy, stay safe.